So I write up a wave function which consists of more than one determinant, which are formed, the determinants formed from some set of molecular orbitals, but I don't determine the molecular orbitals before. I do that at the same time. And that is what multi-configuration or SCF is all about. So MCSCF, multi-configuration self-consistent field. And that already tells you that it is doing a self-consistent field calculation, meaning doing something like a Hartree-Fock calculation. You can also call it multi-configuration or Hartree-Fock. Doing a Hartree-Fock calculation meaning finding the orbitals, but now with a wave function which is not only one determinant, but it's more than one determinant. So our MCSCF wave function is a linear combination of determinants, again, like before, with some coefficients AI. But what I want to stress now, that these determinants obviously depend on some, let's call them CJ, some molecular orbital coefficients. So these are MO coefficients, where these are the determinant coefficients. And now we're going to vary both. We're going to optimize both. So we're using the variation principle, but now we actually vary all parameters in the wave function. Which actually means that MCS is really variational, is fully variational, whereas a CI calculation, a truncated CI calculation, is not fully variational because I don't optimize the MO coefficients. I only optimize the determinant coefficients, not those. So we get them variationally, so I look at the MCSCF energy, or the energy, which is going to be a function of these determinant coefficients, but also of the molecular orbital coefficients. And I take the derivative with respect to determinant coefficient and set it 0, but also the derivative with respect to the molecular orbital coefficients. And set it to 0. Now, this of course is a more complex problem than doing configuration interaction calculations. This, just optimizing the A's, that is what's called linear variation calculation. Like at least most of you probably have seen in some kind of molecular orbital course. So that gives linear equations. But the dependence on the MO coefficients here is not in the same way linear. So that's more complicated. The equation which you end up with, they are just numerically, they're more difficult to converge than either this or that separately. And all that together means that you're not going to have as many determinants or configurations included here as you would have in a CI calculation. MCSCF is really perfect for describing all breaking of bonds. All sort of these degenerate situations with degenerate orbitals or degenerate configurations. That's where this MCSCF approach is really powerful. So it's the method of choice if you have a static correlation problem. Because for the dynamic correlation, that's what we just talked about. For the dynamic correlation, you need those double excited determinants. The one where a pair of electrons described by a pair of orbitals is allowed to perturb each other. So to have perturbed orbitals. But including to having a pair of perturbed orbitals, all the pair correlations, you need to have all double excited determinants. And there's no reason why some orbitals are better than other ones. Some should be preferred over than other orbitals. Why are those two orbitals allowed to correlate and not we? So if you want to treat dynamic correlation, you have to include all determinants of a particular type. Whereas here, you want to have a bond breaking situation. So you should include, you have a degeneracy between two configurations. Then of course you have to include configurations, determinants which describe those two situations. And there is no reason to include a similar configuration but with all the other orbitals. I mean, it's those two orbitals which are degenerate and not this one and that one. So there's a completely, in a way, different aspect of what kind of determinants you should include, whether you have static correlation or whether you're trying to treat dynamic correlation. So for dynamic correlation, you need to include all of the type.